Okay then, so let's continue with our lecture on the next topic, which is on dynamic CMOS logic. So as mentioned previously, there are basically in general two categories of CMOS logic, static CMOS and dynamic CMOS. So static CMOS can be divided into several more categories. So we have the static complementary CMOS, the standard or the classical static CMOS, which is the most common, and then we have the ratio logic and also the pass transistor considered as static CMOS. And dynamic is another class of CMOS logic, and so we'll see what dynamic CMOS logic is all about. So then in dynamic CMOS, in static circuits, at every point in time, except when switching, the output is connected to either ground or VDD via a low resistance path. So what it means by a low resistance path here is essentially your resistance of the NMOS and the PMOS. So there is a path from VDD all the way to ground, connected by the two R equation N, R equation P. In static CMOS, we have the fan-in of N requires 2 N devices, so this is complementary, this classical complementary CMOS. However, in dynamic circuits, rely on temporary storage of signal values on the capacitance of high impedance nodes, requires N plus 2 transistors. Okay, so basically we can say for the same function, let's say for 2 inputs, so 2 inputs, 4 transistors, and for if you implement dynamic, you have a 2 input. Okay, let's put 3 input. So 3 input, 6 transistors. So if you have 3 input on dynamic, you will have 5 transistors. Okay, so if you have a large fan-in design, it might be interesting to consider dynamic circuits. Less transistors means smaller circuit area and probably cheaper to manufacture. So basically the main idea in dynamic circuits, it takes a sequence of pre-charge and conditional evaluation phase to realize logic functions. So it's not like your regular gates whereby you have the input, combinational gate where you have the input generate some output. But in dynamic circuits, you have 2 stages. You have the pre-charge stage and the evaluation stage. So in the evaluation stage is where we evaluate the answer or the output of the logic gate. So let's see example here. So once the output of a dynamic gate is discharged, it cannot be charged again until the next pre-charge operation. Input to the gate cannot make a 1 to 0 transition during evaluation. Output can be in high impedance state during evaluation. State is stored on CL. Okay, so let's have a look here what is going on here. So if you can see the transistor level schematic here on the lower left, this guy. So this is basically your inverter. Okay, okay, so here is your dynamic inverter. So the dynamic inverter contains two NMOS and 1 PMOS. And here phi here is your clock. Okay, sometimes it's called a clock, phi, and A here is your input, and then your output is there. Okay, output Y. Okay, so what happened here is we have the clock here is going to pre-charge, and then it's going to evaluate, and then go back to your pre-charge. So during pre-charge, what happened during pre-charge? Pre-charge 0. So if you apply 0 on the phi there, this one is going to be on. Okay, therefore Y is going to go up. Okay, so Y is going to be logic 1. And A doesn't matter. So A, we don't care what the value of A, because if this is 0, then obviously this is off. Okay, and there's no path to the ground. Therefore, during pre-charge, your output Y is always going to be high. Okay, so during evaluation, let's do some another analysis on the evaluation. So during evaluation, we have our phi is equals to 1. So our PMOS is off, okay, and our NMOS is on. And during evaluation, we have our A is equals to 1. Okay, so if A equals to 1, then what happens is we're going to discharge, and our Y is going to go to 0. Okay, here. Okay, start from here. So as soon as we have the evaluation stage, the start of evaluation stage, and it checks that our A is 1, immediately Y is going to go down to become 0. So it's basically an inverter. Okay, so but when A goes back to 0, okay, when A goes back to 0, it should rise, but it doesn't rise. Okay, the reason is because if you put 0 here, this one is 1 here, this one is off. Okay, because your evaluate is off. So during evaluation, only one transition is allowed. So it's not like a normal inverter. Normal inverter, whenever you give a 1, your output is 0. Okay, you give a 0, your output is always going to be 1. But for dynamic circuits, during evaluation, you evaluate only one time, which is the first time, and that's it. Okay. Okay, so this is what happens. So during evaluation, we have your output Y is equals to 0. So the key idea here is that in dynamic circuits, you don't have A and Y only. Okay, this is your input. Okay, here is your output. So you don't have input and output, but you also have a clock signal, the phi clock signal, where during pre-charge is going to be 1 on the output, and then during evaluation we are going to see what is going to be the result of the output. Okay, so what is the properties of dynamic gates? So logic function is measured by the PDN only. Number of transistors n plus 2 is seen already. Should be smaller in area than static CMOS. Okay, especially for if you have a large n, right? If you have a small n, small fan in, then maybe it's small fan in, maybe the static CMOS is less transistors. Full output swing, so BOL ground, BOH VDD. Non-ratio sizing of these devices is not important for proper functioning. Proper ratio is done only for performance. And faster switching speed, okay, especially during the pre-charge, right? So during pre-charge, it charged just through the PMOS, and then if the evaluation stage doesn't change, then basically you have propagation delay equals to 0. So reduce load capacitors due to lower number of transistors per gate, reduce load capacitors due to smaller fan out, no short circuit current, so all current provided PDN goes into discharging the CL. TPLH0, this is the key thing here. So the time to charge the output node is essentially 0, because during pre-charge we already set the output to be equals to 1. So if the evaluation later on is evaluate to 1, but it's already 1, so basically we don't need any additional time to evaluate to 1, therefore your TPLH equals to 0. However, the TPHL might be slow. Okay, TPHL can be slow because we have additional transistor for evaluation and pre-charge. So what else do we have here? Power dissipation should be better than the static CMOS. It consumes only dynamic power, no short circuit power consumption, since the pull up path is not on evaluating. Lower CL, by construction can have at most one transition per cycle, no glitch. Okay, but power dissipation can be significantly higher due to higher transition probabilities and extra load on the clock. Okay, so basically what happened is your dynamic power is very high. Okay, because you keep on at a high rate, you keep on pre-charge and evaluate periodically. Okay, so we keep on pre-charge, evaluate, lots of time, many times with a certain pre period. The transistor keeps turning off and on quite frequently, so your dynamic power is pretty high on dynamic gates. The pull-down network start to work as soon as the input signal exceeds VTN, so VM and VIL all equal to VTN. The noise margin low is small. Okay, the noise margin low is small is because our noise margin high is huge. Why is huge is because basically there's no time we need to charge the node because it's already pre-charged. Okay, and another issue is we need a pre-charge clock. Okay, so normal gate we just have input output, and for dynamic we need a special pre-charge clock. Okay, so dynamic CMOS is not perfect. I mean, it's trying to overcome the limitation in static CMOS because we don't want static power. Okay, we don't want the devices to be the PMOS and NMOS to turn on at the same time. So to avoid this, that's why they come up with the dynamic design. But of course, there's no free lunch. Okay, there's no free lunch. When you take away something, okay, you take away the static power, the static current, and now your dynamic is higher, and you need a clock signal, and there are many issues. There are several issues with the dynamic design. That's why actually dynamic design is not really frequently used as compared to static. I mean, static, the standard static CMOS is the de facto standard still. So I'm not going to go into too much detail on dynamic design. It's not it's not widely used today, so it's not so relevant. But it's nice to see what the kind of designs that people do, what they think, how they think to overcome some of the limitations in the current device. Okay, so the first one is the charge leakage. So in dynamic CMOS we have a leakage of current. Okay, current leakage, so voltage leakage. So the leakage occurs here during after pre-charge. Okay, so after pre-charge it's going to drop down, and then during evaluate it's going to drop down. Okay, and it's discharging through the reverse bias diode here. I think it's okay. So it's a reverse bias diode. Okay, so there is some issues there. So the impact of charge leakage, the output settles in the intermediate voltage determined by a resistive divider of the pull up and pull down network. So we can see that as we give the evaluation clock here. Okay, so this is the eval. The output is actually going to drop. Okay, the output is assuming during eval that the output doesn't change. Okay, it's maintained logic 1, but your output actually for some reason it drops. Okay, so how to overcome the charge leakage? Of course, people come with a solution. We can solve this, okay, using something called the keeper. So the keeper compensates for the charge loss due to the pull down leakage path. Must be weak enough not to fight evaluation. Same approach as a level restorer for the PT logic. So the keeper, what it does is basically your output here is logic 1, and it's going to drop. Okay, let's say 2.5, it drops to 1.8, and what happened here is this is going to be logic 0, this is on, and here is connected actually. So here is going to go back to 2.5, and we have a full swing. Okay, issue number 2 is a charge sharing. So in charge sharing, let's see. So it is possible for delta V out to be large enough to cause circuit malfunction. V out drops to become logic low instead of remaining at high. Okay, so so this is another issue. So during pre-charge is okay. Okay. So this is during evaluation, right? So during evaluation where your so your clock equals to 1. Okay, your clock equals to 1. This is off. Okay, this is during eval. So this off, and we are trying to discharge, and we can see that actually is discharging to CA, okay, and if B is on, then it's going to discharge through CB. So your CL is going to be CL reduced. The V, the voltage on CL basically is reduced, okay, because it's shared. The voltage now is actually shared with CA or CB, okay, in this case CA, because B is 0. So if A is 1, then some of the charges this is charge, okay, the charge on the capacitor, so the charge actually gets transferred to CA, okay. Charge stored originally on CL is redistributed over CL and CA, leading to static power by downstream gates and possible circuit malfunction. Okay. Example waveform is with charge sharing problem. So let's have a look quickly here what's going on. So we have the phi, okay, the clock here, going into the eval, so it's going to 1. Okay, so it's going to 1. So what happened when it's equals to 1? So this is off, and it's going to discharge. Okay, and your A during eval, your A is going from 0 to 1. Okay, it's going up. Okay, so A is going up. So what happened when A is going up? So when A is going up, this is going to be on. Okay, at the moment it's going up, it's going to be on, and B is 0, so this is off, and here is on. Okay, we give a 1 there. Okay, okay, so this is off, this is on, this is on. So if transistor A is on, therefore your charge on CY is going to go and share with CX. So we can see that your Y actually drops. Okay, your Y drops a little bit, and your charge on X is going to increase, and this is going down. Okay, is that what we want? It's not really what we want. Okay, ideally when we give a 1 on A, we want Y to be constant, right? We want Y to be logic 1. We don't want to have any drop in the voltage. So there's some stability, reliability issues there. Some of the charges, get transferred to somewhere else. Okay. Charge sharing example. I think I'm going to skip this one. I don't want to go into too much detail on these alternative CMOS structures. So just good to understand that there are different CMOS structures besides the normal static CMOS, and to see the thinking behind to overcome some of the limitations in static CMOS, and then what are the issues with the solutions, and how we overcome them. Okay, so solution to the charge redistribution, pre-charge internal nodes using a clock driven transistor at the cost of increased area and power. So we add one more. Okay, we add one more, and here we purposely, so let's say okay, so let's say this is 0 during pre-charge. So during pre-charge, we are going to charge the intermediate node. Okay, charge intermediate nodes. Okay, because the intermediate node is not charged before. Okay, because there's no charge in the intermediate node, then your charge from your main output node is going to be shared with the intermediate. So let's charge the intermediate, so it cannot be shared later on during evaluation. Okay, number 3, backgate coupling, susceptible to crosstalk due to high impedance of the output node and capacitive coupling. Out2 capacitively couples with out1, so the gate source and the gate drain capacitance of M4. Okay, so let's see where's M4. So let's see if we have something here. Okay, so we have the crosstalk. So the crosstalk is a noise that is generated between two parallel wires. Okay, so two parallel wires, we are talking about the capacitance of M4 between out1 to the gate source. Okay, out1 to the gate and the source, which is here, and then out 2 between the gate and the drain. Okay, so you have a crosstalk between those two. Okay, because we have this node here that we didn't have before in static CMOS. Okay, and this node is connected to out2, and then we have 2 parallel wires together creating a crosstalk and some noise. Okay, some noise in the signal. Okay. Capacitive coupling means out1 drops significantly, so out2 doesn't go all the way to ground. Okay, that's the issue. Issue number 4 is a clock feed-through, a special case of capacitive coupling between the clock input of the pre-charged transistor and the dynamic output node. Okay, so we have another capacitive a capacitance there between the clock and the out. Coupling between out and the clock input of the pre-charged device due to the gate drain capacitance. So voltage of out can rise above VDD. The fast rising and falling edge of the clock coupled to out. Okay, so here is another, you can say, parasitic. Okay, so another parasitic that's created there. So it creates another issue where your output can go above VDD. Okay. Okay, so cascading dynamic gates. So if you put the two, so this is your inverter. Okay, so here is your dynamic inverter 1, dynamic inverter 2. Okay. So putting them together, basically look something like this. If you want to visualize it, and here you have the phi, and here you have the phi. Okay, so in dynamic you have 2 input actually. Okay, you have the in and the phi or the clock. Okay, here is your phi. Okay. Okay, so if we for example, if we put a logic 0 here, we're expecting a 1, expecting a 0 there. But remember, the evaluation only happens when your CLK or your phi is in the evaluation mode, which is equals to 1. Okay, so the evaluation occurs right here. Okay, so we are going to evaluate the output of the buffer or the inverter during the evaluation stage, and it's checking only once on the first time only, and any changes later after that it's not going to take into account. Okay, so during the evaluation we see that in equals to 1. Okay, so in equals to 1, we're expecting a 0, expecting 1. Okay. So what happened here is out 1. Okay, out 1 is here, and out 2 is there. Okay, so out 1 correctly goes to 0. Okay, nice. This looks good. It doesn't go all the way to 0. It goes to VTN, in fact. Okay. Sorry. No, it actually should go to 0. Okay, so it should go to 0. VTN is right there. Okay, right before it goes to 0. So the thing is, as out 1 reach VTN. Okay, so as out 1 reach VTN, out 2 is going to stop going down. Okay, so out 2 is going to stop going down, stops decreasing, because okay, so if this is 1, if your clock is 1, so this is off, this is off, this is on, this is on, and in is 1. Okay, in is 1, this is on. And what happened to this guy? Okay, the out 1 transistor. Okay, so out 1 is going to drop all the way to 0. So this one is essentially, you can say, is off. Okay, initially it's on. Initially it's in on state, and then gradually it's going to go down, and actually when it reach VTN it's going to stop because it's off. Okay, so is it a buffer? It's not really working as a buffer. So to overcome this cascading dynamic gates problem, they created what is called the domino logic. Okay, so domino logic is more stable. Okay, just like the transmission gate in the pass transistor, TG is more widely used, and for dynamic logic people like to use the domino logic. Okay, so what is the domino logic? So here is one domino circuit. Okay, if you consider this, so you have the dynamic logic plus your static CMOS inverter. Okay, so here is your static CMOS inverter. Okay, when you combine your dynamic logic with the static CMOS inverter, you get the domino gate. Okay, the domino gate. Okay, so what is the issue here with the what is the deal here with the domino gate? So in the domino gate, let's say you have a 1-to-1 transition and a 1-to-0 transition during eval. Okay, during evaluation. If it's 1-to-1, the output here is going to be 0-to-0. Okay. Okay, the output here is going to be 0-to-0. If you have a 1-to-0 transition, okay, the output is going to be 0-to-1, and it's full swing. Okay, full swing, and but now the output is actually inverted, because if you transition from 1-to-1, if you think of like an inverter is putting an input 0. Okay, putting an input 0. So putting an input 0 as an inverter, for example, and you are getting back your 0, okay, on the output of the domino logic. Okay, so you might need another inverter at the end if you need a 1. Okay, else it becomes like a buffer. Okay, so domino logic is interesting. Let's see. Okay, so here they do a domino logic with the restorer. Okay, with the level restorer there. Okay, so follow dynamic stage with inverting static gate. So dynamic stage plus the inverting static gate. Dynamic static pair is called the domino gate. Produce a monotonic output. Each gate triggers the next one like a string of dominoes toppling over. Okay, so why it's called domino is because if you see the timing diagram down here, is propagating through. Okay, so during eval is going to send here, and then generates a W. Okay, W, X, Y, Z is there. So four cascading gates, and then and it's going to go through serially one by one. So it's going to knock over this one, knock over, and knock over, and finally you get your output. Okay, and also in pre-charge as well, you send and knock this over, knock this one, and this one together, and then this one. Okay, so here is the flow. Okay, here is the flow. So what happened here is we can analyze this. So we want to see what is the output W, X, Y, and Z during the evaluate stage of the domino logic. Okay, so A and B is given. Okay, given a certain A and B, let's say your W here is given based on the values of A and B. So we get a certain W, and during evaluate, your W goes down. Okay, so your W goes down during evaluate, and your X will go up because you have the inverter here. Okay, if you can see the inverter there. So your X goes up after a certain delay, certain combinational logic delay. So X goes up, goes to logic 1. Okay, goes to logic 1, and then it goes through another set of domino. Okay, it goes another set of domino to the output Y, and the output Y goes down after a certain delay, and then you have the Z is the output is another inverter. It goes to logic 1. Okay, so that's basically how the domino logic works. One thing that we can take from here is that when you talk about dynamic CMOS, it's not like a regular logic gates. It's not really widely used, so maybe it's not so common. Maybe you have not heard it. But in dynamic CMOS, you have the pre-charge and evaluate. This is the key thing here. Okay, and pre-charge, we assume or we set the output equals to 1. Okay, we always set the output equals to 1. and during evaluate we can check, is it 1 or is it 0. If it's 1, we don't do anything. Okay, so TPLH is 0, and then if it's 0, then we need to discharge. Okay, and it happens only during the evaluate stage. Okay, so as a summary, Domino logic is attractive for high-speed circuits, 1.3 to 2 times faster than static CMOS. However, there are many challenges, especially the dynamic power, leakage, monotonicity, charge sharing, noise, coupling, crosstalk, and so on. Widely used in high-performance microprocessor 90s, when speed was king, when everything was about speed. The speed issue is mainly because we have the pre-charge. Okay, the pre-charge, we set the output equals to 1 before we know the actual result. Okay, if the result is 1, good. Okay, super fast. But if the result is 0, then it goes down. I mean, we need some time to discharge the node that we already charged to 1. Okay, that's why it's super fast, because we predict the output to be 1. So if you have a circuit that the output is always, a lot of the output is always 1, you might want to consider using the domino logic. But largely is replaced by static CMOS now that power is a limiter. Okay, now everything is you talk about power, mobile device, and so on. However, according to this note, it's still used in memories for area efficiency. So I'm not sure if it's true today or not. I don't think so, but I might be wrong. Okay, so how to choose a logic style? You must consider the ease of design. Okay, so what logic style have we looked at? We have looked at the normal static CMOS. We have looked at the ratio logic. There's a couple of different ratio logic you can consider. There's pseudo NMOS, there's a depletion region, active load, resistive, and then there is a pass transistor, there is a transmission gate, dynamic logic, domino logic. Okay, so you must consider which logic style to use. Of course, majority is using static CMOS. It's stable. The power is not so bad. Okay, but you have a nice stable VM, nice VOL, VOH, and so on. Nice noise immunity with the static CMOS. So that's why people prefer that one. But of course, you can also consider the other MOS logic. Okay. So here it says the current trend is towards increased use of the complementary static CMOS, design support through EDA tools, robust, more amenable to voltage scaling. Okay, so it's easy to go for scaling. Synopsys, Cadence, they all support the standard cell libraries. As far as I know, the standard cell libraries, maybe like 90 or 99% is based on static CMOS, okay, rather than dynamic or pass transistor and so on. Okay, so that's it for this chapter and for this week. For the next topic, we'll look at the speed and power optimization.